Okay, let's dive right into this explainer and deconstruct a truly fascinating, absolutely high-severity Linux privilege escalation vulnerability. It's known as copy fail. Now, if you are a software developer or maybe a junior to mid-security engineer, this is an explainer you're going to want to pay close attention to. We're looking at CVE 2026-31431. It's a logic flaw that literally broke the security boundaries of virtually every major Linux distribution for nearly a decade. Today, we're breaking down exactly how a tiny little script can grant full root access in seconds, entirely in memory. Let's get into it.
Before we get into the deep technical weeds, I want you to consider this quote. David Brumley from BugCrowd pointed out that zero-day exploits like this one, they tend to sell on the broker market for the price of a house. Why? Well, because universal, Linux, local privilege escalations that require absolutely no race window, no per-kernel offsets, and provide a perfectly clean container escape primitive are just exceptionally rare. So this isn't just another everyday bug. It represents a fundamental ground-up breakdown of shared kernel isolation.
Here's our roadmap for the explainer today. We're covering the overview and design intent, the root cause, the exact attack flow, the impact and scope, how it was discovered, and finally, some actionable mitigation and key lessons.
All right, Section 1, Overview and Design Intent. Let's understand what we're actually dealing with here.
So copy fail carries a 7.8 high-severity CVSS score. But honestly, do not let the lack of a 9 or 10 fool you here. In plain, everyday language, this vulnerability allows any unprivileged local user on a Linux system to trivially gain full root access. It does this by corrupting the in-memory cache of privileged files, effectively hot-patching set UID binaries while they are running, and here's the crazy part, without ever actually touching the physical hard drive.
To really grasp how this happened, we have to look at the original design intent of the vulnerable component, which is AF_alg. This was built to give unprivileged users safe, high-performance hardware crypto acceleration, right? The underlying assumption from the developers was simply that user space applications would only be able to interact with the loud cryptographic algorithms and that the memory buffers being passed back and forth would be safely isolated. But, as you'll see, a relentless pursuit of extreme performance eventually shattered that assumption completely.
Moving on to Section 2, Root Cause and Abstraction. Let's see exactly how this well-intentioned design failed. First things first, we must understand the page cache. Think of the page cache like a public reading room in a library, where everyone can come and read the master copy of a super popular book. It makes reading incredibly fast. But the strict rule is that no one should ever be able to write in that master copy. The vulnerability class we're dealing with here is an incorrect resource transfer between spheres, specifically CVE-2026-31431. Broadly speaking, these types of logic flaws happen when two isolated systems interact in a way that violates a core security invariant. In our analogy, it's failing to write protect that public library book. The real turning point happened back in 2017. A commit 72548B093E3 was introduced to optimize memory during decryption. It allowed the kernel to reuse source memory as the destination, basically chaining the source data directly into the destination mapping to save processing time. By doing this, they effectively handed our library reader a pen and gave them permission to write directly onto that read-only master copy. It took a read-only page cache reference and dumped it straight into a writable destination buffer. But here's the thing, that optimization alone wasn't quite enough to cause the exploit. The root cause analysis shows it collided catastrophically with the often synonymous cryptographic algorithm. See, this algorithm requires a tiny little bit of scratch space to temporarily shuffle data around during its calculations. So it blindly writes 4 bytes of scratch data past its legitimate output boundary into what it assumes is a perfectly safe user-owned destination buffer. But because of that 2017 optimization, that destination buffer is actually pointing to the global host-wide page cache.
Okay, Section 3, the attack flow. Let's walk through the mechanics of how an attacker actually exploits this logic.
Here is the exact step-by-step sequence. First, the attacker uses a tiny 732-byte Python script to open an AF_alg socket. Second, they craft a payload, cleverly hiding 4 bytes of malicious shellcode inside the associated authenticated data of a network message. Third, and honestly, this is the magic part, they use the splicing system call to pipe a privileged target binary, like USR bin SU, directly into the crypto socket. Splicing passes the page cache references of that binary straight to AF_alg. Finally, the attacker calls receive message. The algorithm executes, writes its 4 bytes of scratch data, and overwrites the target binary directly in the system's active memory. The attacker just loops this until their payload is fully staged, then they execute USR bin SU to get a root shell. It's wild.
Let's jump to Section 4, Impact and Scope. Just how massive is this breach? Because this flaw literally sat in the mainline Linux kernel for almost 9 years. The verified vulnerable platforms include virtually every single mainstream Linux distribution shipped since 2017. We're talking older LTS lines, kernel versions 4.14 all the way through to 7.0-RC. Now, while the exact numerical scale of compromised hosts is inherently a bit uncertain, researchers estimate this exposed millions of Kubernetes clusters and cloud-based workloads globally. And what really makes the impact so severe is the stealth factor. Because this specifically corrupts the page cache, the attacker gets in-memory execution of root privileges, UID 0. The actual physical file sitting on the hard disk, it remains completely untouched. The kernel never marks the corrupted pages dirty for write-back. This means standard file integrity monitors that are just hashing the files on your disk are going to report that everything is perfectly fine, even while a completely compromised version of the binary is running right there in active memory. And we're already seeing real-world exploitation. CISA has officially added copy-fail to its known exploited vulnerabilities catalog. Crucially, because the page cache is a shared resource across an entire host, this vulnerability acts as a truly catastrophic container escape primitive. If an attacker breaches a single, restricted web container, they can just use this flaw to overwrite a binary on the underlying host node. That completely breaks Docker and Kubernetes isolation, letting them take over the physical machine. All right, Section 5, Discovery and Impact. Let's talk about how AI is changing the bug bounty game. What is just truly staggering to me here is the discovery method. This flaw hid in plain sight since July 2017. It evaded human fuzzing, it evaded top-tier code review for nearly a decade. Yet, the Theory research team used an AI-powered code auditing tool called ZincCode to uncover it in just 1 hour of scan time. Seriously, 1 hour. This proves that the cost and time required to find deep kernel logic flaws have dropped by an order of magnitude. It's really forcing the security industry to realize that the window between a vulnerability's existence and its discovery is shrinking incredibly fast.
Finally, Section 6, Mitigation and Lessons. Let's talk about actionable defense.
The vulnerability was officially fixed upstream by commit A664BF3D63D. And this patch is honestly beautifully simple. It completely reverts that flawed 2017 optimization. By forcing the cryptographic interface to go back to operating out of place, the fix safely separates the read-only page cache references from the writable destination buffer. That instantly neutralizes the vulnerability. So, first things first, you absolutely must update your kernel packages immediately to versions that include this fix.
Now, for the developers out there managing CI/CD pipelines, I know you cannot always afford to wait for long patch cycles. So here are your immediate actionable steps. First, if it's possible for your environment, blacklist the algif aad kernel module locally. Second, audit your own code to see what is actually using this interface. Just run lsof, grab aflgog in your terminal. And finally, for your CI/CD runners, like your self-hosted GitHub Actions that might be executing untrusted pull requests, you must implement seccomp profiles that explicitly deny the creation of afgog sockets. Doing that breaks the very first step of the entire attack chain. And for the junior to mid security engineers tuning in, your primary lesson today is that namespace containers are not a hard security boundary. Never have been, never will be. You must treat any container remote code execution as a potential full host compromise. To hunt for indicators of compromise in your production environments, you should be deploying eBPF. That's the Extended Berkeley Packet Filter, to monitor for unusual or unexpected AF_ALG socket creations. Standard endpoint detection might totally miss the memory overwrite, but eBPF can catch the highly specific repetitive socket and splice system calls that the attacker literally has to use to inch their way through the file cache.
As we wrap up this explainer, I want to leave you with one final thought to chew on. We've just seen how a totally well-intentioned performance optimization became a devastating exploit and how an AI surfaced it in a matter of minutes. If tools can find bugs like this so incredibly quickly today, the baseline for what constitutes a safe system has fundamentally moved. So ask yourself, is your shared kernel multi-tenant architecture truly secure, or is it finally time to seriously consider hardware-level VM boundaries? Thank you so much for diving into this complex vulnerability with me today, and stay secure out there.